So now let's take a look at some equations that seem, well, a little bit more on the difficult side. Here's one. We've got 2 sine of x times cosine of x equals radical 3 times the sine of x, and we're looking for all of the values of x that will make that equation true on the interval from 0 to 2 pi. Our goal here really is to find a way to factor this apart, isolate parts of this trigonometric expression from the other so that we can get a nice simple one like our sine of x equals 1/2 kind of business that we saw in the last examples. And the real key to doing this one here is this. When we have multiple mixed parts of an expression, just like when we were solving polynomial equations, we're going to set the equation to 0. So our first task right here will be to set the equation equal to 0. So when you have multiple parts, and it's not just a simple sine of x is equal to something that we can isolate really easily, set it equal to 0. And then let's see if we can isolate a part by factoring. So in this case, I'm going to subtract square root of 3 sine of x from the left and the right hand side, so that I'm going to get a brand new equation, 2 times the sine of x times the cosine of x minus the square root of 3 times the sine of x is equal to 0. And you'll notice that I have a common factor right away from these two terms on the left-hand side, and that is sine of x. So now I'm going to factor it apart. And this is an awful lot like what we were doing when we were solving polynomial equations, right? We would factor out the common factor and ask ourselves, well, what would we have to multiply by sine of x to get our first term? And that turns out to be 2 times the cosine of x. And we say sine of x times what would give us the second term right here, and that just ends up being the square root of 3. And so we actually have 2 equations. We set each factor equal to 0, so we get sine of x is equal to 0 as one of our potential areas, and the other one where 2 cosine of x minus the square root of 3 is equal to 0. All right, so now we ask ourselves, at what values of x will we get 0? Well, the way we're going to deal with it, of course, we can say that if we take the inverse sine of 0, we're going to get a basic value. And we find that x equals 0 is one of those values. Well, this is actually a quadrantial angle along the horizontal axis, and we know that sine of x is equal to 0 at those quadrantial positions. So our other position would be at x equals pi minus the reference angle. We're taking 0 to be a reference angle, so x equals pi would be our second angle that makes this true on the interval from 0 to 2 pi. Now the other one's a little bit more complex, but not so much so, because we know that if we added the square root of 3 to both sides, and then divided both sides by 2, we're going to find that we're going to have a cosine of x, some angle, equal to radical 3 over 2. Well, kind of like what we did on inverse sine, we can use an inverse cosine, and that's going to give us a nice first quadrant angle whose cosine would be positive root 3 over 2. Remember, inverse cosine will give us angles in either the first or the second quadrant. Since it's positive, that's quadrant 1 only, so quadrant 1, inverse cosine of radical 3 over 2 happens to be pi over 6. But what else could we say? Well, this is quadrant 1, so what is the other question? At what other quadrant is cosine positive? And that turns out to be quadrant 4. So to find our quadrant 4 angle, we're going to take x equals 2 pi minus pi over 6. Treating pi over 6 as the reference angle gives us x is equal to 11 pi over 6. And so our solution set is going to be a set of 4 numbers on the interval from 0, including possibly 0, all the way up to 2 pi. Will be the solution set 0 in order pi over 6, pi, and then 5 pi over 6. So we have 4 separate solutions on this interval from 0 to 2 pi. And that's the kind of thing we're looking for.